So is this an annual hackathon thing you do, or is this the first year you're doing it?
Yeah, this is an annual event. This is our 4th time organizing it, the first time going virtual. I believe that one year we hosted 2 events. So
we are live, guys. Sorry to interrupt you, Kathy. Nina, here is the YouTube link in case you need to share it with Jackie. I'm going to share it on the Slack channel as well.
Can you see my full screen?
Yep, we can, Nina.
I'm going to start the webinar now. Kathy, feel free to start recording whenever you're ready.
Okay, so should we start, I guess?
let's wait a couple minutes for people to filter in. We'll officially start at 9:05.
Oh, perfect. Okay.
Thank you. We're going to be starting on MIT time, 5 minutes past everything. All right, actually, I think we have most people online, so let's get started. Good morning, everyone, and welcome to day 2 of the MIT Policy Hackathon. I hope you had a great time last night. It was a pleasure to hear from Shabata for our opening keynote address, and today I'm very excited to present to you our presenters from Brattle. Brattle is an economic consulting firm that uses data analysis to inform decision-making for lawmakers and various clients throughout the world. And I actually have quite personal connection to Brattle in that I worked there for 4 years prior to coming to MIT. So that was a really great experience. And I'm really excited to present to you today our speakers, Evan, Natalie, and Anna, who will be talking to us about a recent analysis that they've done using nurses' health data. So the floor is all yours.
Thanks a lot. So my name is Evan Cohen. I'm a principal at the Brattle Group, like Kathy just said. I'm presenting with my colleagues, Natalie Hinchy and Anna Heffernan, some work we've been doing using the nurses' health data, which, as we'll get into, is probably the largest and most influential epidemiological study undertaken over the last 40 years. That's been quite influential in a lot of health and public health policy over that time period. And what we're gonna present as we're gonna get into is some of the pitfalls that we've discovered in working with a data set this large. And so we're going to be monitoring the chat. Feel free to post up your questions. One of us will try to interject those questions into the presentation. And we are planning to publish these results sometime soon. These have not been, you're really the first audience that's seeing this data and this data in this way. And we're, this is kind of a dual purpose. We're definitely looking for feedback from all of you. And so we're excited to get started. With that, I'll turn it over to Natalie.
Thanks, Evan. So Anna, I guess we'll go to the first slide. So as Evan was saying, we're focusing on large data sets. And big data sets and our ability to process them are a relatively new phenomenon, and they present many opportunities for researchers. But at the same time, they do present serious pitfalls that we want to highlight to this audience. And we want to try to present some solutions to try to ensure against falling into these traps and give some robustness checks to ensure that inferences that are drawn from big data sets are valid. So what motivated our research, as everyone was saying, we had access to a very large data set, tens of thousands of observations. And we started playing with this data. And we noticed what we like to call the cloud, and that's that figure on the right. What the cloud is showing is the average caloric intake for people against their BMI. In other words, it's showing us how much people eat and a measure of how big they are. Like many other people, I thought that the more one eats, the more one weighs. What we saw in this data set was that relationship really didn't pan out. There was no discernible relationship between the two variables. What was striking to our team was how easy it was to estimate a statistically significant relationship between these two variables. And that's what we're going to discuss in our presentation today, is this problem that big data presents, that it's very easy to draw conclusions and inferences when you have a lot of data in relationships that don't actually really exist. And this is especially important when we have a bias going into the research, like the relationship between calories and BMI. Frankly, I was shocked to see this relationship the first time I did. So the two things we're going to highlight today are the dangers of relying on big data sets and different ways we can try to ensure that we don't fall prey to these dangers. So Anna, do you want to discuss the outline of our presentation?
Of course. So today, like Natalie said, we're going to take you through the pitfalls of big data that we are firsthand seeing in the nurses' health data. And through that, we're going to start with looking at some of the summary statistics and how we chose the data we are currently using in our analysis, as well as showing you some graphics on why we chose the regressions we did and which ones we ended up keeping in the analysis.
So I've been at Brattle for 12 years. In 2011, I began a research group that was looking at how we can apply some more advanced data analytic methods to data sets that are pretty widely used in the industry. And the first data set we tackled was a US government data set that was not longitudinal, meaning each year they did it, they got a brand new sample, a brand new cohort. And we published the results of that analysis in a nutrition journal in 2015. We did not choose to continue working with that data set because it was small, it was non-longitudinal, it was very noisy because it was small. The participants were never more than a few thousand in any given year. And then, because we're trying to bring some analytical firepower to data sets, we started looking in the last few years for data to analyze. And we were really happy to come upon the nurses' health data, which is widely considered the largest comprehensive longitudinal nutritional health data set in the world. There have been over 3,000 studies that have been published using this data, and it's been influential in all sorts of public policy recommendations, both from scientists and from government. Most notably, it is one of the cited studies for the US dietary guidelines that influence federal subsidies and everything from school lunches to food stamp use, and really sets the gold standard in the United States and in the world for what epidemiologists and nutrition professionals are recommending that people eat. And that's just why it's so vital to understand these data sets and understand what they're telling us and really what they're not telling us. So the nurses' health data has been run since 1980 through the Harvard School of Public Health and Brigham and Women's Hospital, which is a world-class clinical and research institution in Boston. In the beginning, they recruited the first cohort in the late 70s, which had about 100,000 female nursing professionals. It is not a representative data set, as in one limitation in working with this data is it is neither demographically nor gender-wise particularly diverse. We're working with a companion study that also has men in it, but researchers always have to caveat that these are 93 to 97% white female nursing professionals who come with their own socioeconomic and demographic backgrounds. We're going to focus here on the Nurses Health 2 study, which began in the early 90s, and it recruited over 100,000 female nurses. And we're using this because over 100,000 women were recruited, and the way the survey worked was there were some initial benchmarking on height and weight and a whole bunch of other demographic statistics and also health statistics where they collected blood work and prescriptions, physical activity, smoking status, you name it, it's in there. And then they followed up with these same women, and they had really, great retention rates for a survey of this size, of keeping up with them for going on 30 years now. We're working with the latest data, which, there is a big lag between data collection and data availability. So our results today are only through 2011, but I think the focus of this presentation on those pitfalls are going to be really extendable to future future data when it comes out. And so that's kind of the nurses' health data. We were really fortunate to put in a proposal and be given access by the Harvard School of Public Health. We've been working with it for 2 years, and are going down a number of different paths with it. But right now, what we're looking to do is verify the trends that we observed in the other data set, the NHANES data set that you'll see interspersed in some of our slides, and take a look at the kind of inferences that can be drawn with this data in terms of statistical reliability. So with that, I think I will turn it over to Anna.
Me. Yes, so as Evan said, this is about 20 years of longitudinal data. And so a problem that we'll have in data like this is a sample will age out pretty quickly. And when you're looking at factors like weight gain or caloric intake, when you look at older respondents, they don't follow traditional weight patterns. And so something we wanted to address was, we actually didn't want to have to address that, so we removed them. So our sample contains like normal adults. So anybody over, I think the earliest person, 1991, is around 25, 26, and we have a cutoff at 64. So no one older than 64 gets into our data. So we want to control for age in a way. We want to limit to non-pregnant and non-lactating women whenever we can, although in this data, like in all big data, we do have some data limitations where there are sometimes variables that are missing or seem incorrect. And so we've had to adapt methods to figure out how to adapt our data to either exclude these participants that might have a data error or just find a way to include them. NHS2 is pretty good in this respect. So if you see in the second column, the total number of respondents, these are everybody that are in NHS2, and the respondents in analysis are everybody we're keeping. So we only eliminate a few hundred respondents in every year, which is much better than some of the other longitudinal data sets where if you start when you're 25 in a year at the very youngest, and this goes up to 50, if the longitudinal study is 30 years, you're going to age out pretty quickly. So NHS2 is a really good data set for keeping a lot of respondents in our analysis. And we really have a focus on BMI and calories. And this is one, like Natalie said at the beginning, this is a relationship you hear of very often. It's probably the most common relationship you hear when you hear about diets or just nutritional trends. And so to kind of control for the missing data problem, we only kept respondents who had BMI and calorie information. They were eliminated regardless of what other information they contained. And so with this, we're going to look at some of the BMI and calorie trends, or if you want to call them trends, we're going to look at the relationship basically of BMI and calories. And I think that you'll be surprised over what we found, because I know we were. With that, I think I turn to Natalie.
Actually, I think the slide's mine. I know Natalie had introduced BMI, body mass index. I want to make sure that that everybody understands what that is. Body mass index takes your weight and your height, and through kind of a pretty simple transformation comes up with a number. And the higher that number, the bigger you are given your height. So for most people, it's a pretty decent measure of a healthy weight versus overweight, obese, and severely obese. For somebody like Dwayne "The Rock" Johnson, who's a lot of muscle, and he's going to show up fairly high on the BMI. He probably shows up pretty close to the obese category, but I don't think anyone would look at him and say obese. So the BMI measure does have a little bit of limitation, but for data like this, generally extendable to large populations, it's a really good measure of sort of a healthy weight versus getting into some of those more unhealthy weight where there's a lot of comorbidities. And so I just want to make sure, because we're going to be focusing on BMI in this presentation, that we gave a little bit more color. So here, the first data we're presenting is just the Nurses Health 2 data in blue. You'll see it started in 1991. And what it shows is that NHS2 nurses are eating around or reporting they're eating around 1,800 calories a day in most survey years. You'll see a little drop off after in the last year in 2011. But the red dots are the NHANES survey that we previously published, which started in 1971. And you'll see there is all the data really shows, regardless of the reporting method, that there has been a big jump in caloric consumption before and after 1980 is kind of the pivot point, because that's the first year the US Department of Agriculture issued their dietary recommendations, and it was coincident with a big transformation in the American diet from more fat-based to more grains and carbohydrate-based. And we see that this data indeed is quite consistent with the trends we're finding that we published in the NHANES data. We will caution that these dietary surveys are historically unreliable. They're self-reported, and their data collection methods are always suboptimal. I mean, the way you really want to do this in a clinical setting is to have the survey participants eat the measured food that the researchers are giving them, so they know precisely their mix. And instead, they're just asking them to recall. These are called dietary recall surveys, to recall what they were eating over a certain day or a certain time period. And with that comes certainly a little bit of bias, where survey participants generally are found to underreport their caloric consumption, simply because they kind of want to give researchers the answer of what they think they should be eating. But in any case, what this data shows is that there's relative consistency in the data across surveys in terms of the reported caloric consumption. I think Natalie has the next bit of data.
Thanks, Evan. So what was interesting to us is, as Evan pointed out, caloric intake did seem to increase from the 1980s to present time. But starting in about 1990, we're seeing the trend that the caloric intake didn't change by that much. There is slight fluctuation between the years, but it seemed relatively constant. When we compared that to the increase in BMI over time, that's when we really started to get interested. So what we did is we looked at 3 different data sets. The first was the NHANES data set that Evan just discussed. Then there was the NHS2 data set. So that's the Nurses Health data set that we've been focusing on. But we also included a third data set called NHS1. And that's a similar data set to NHS2, but it started with an earlier cohort. And the reason we did that, I'll explain the reason we did that in just a minute. But I want to draw your attention to this figure on the left first. And what we're noticing is that in 2 of our data sets, the NHANES data set and the NHS2 data set, we're seeing a pretty significant increase in the average BMI of the respondents over time, starting in the 1990s. Well, actually starting in 1970, but we're seeing the trend continue throughout the entire time period. So we should contrast that with the fact that starting in the 1990s, we didn't see significant changes in caloric intake. So when we were thinking about this, we had to consider the fact that we were dealing with a longitudinal data set. So it was very possible that the reason we were seeing this increase in BMI was because our respondents are aging over time. Generally, as people age, they tend to become bigger. So to try to account for that, we took a specific age group within our data set, and we tried to see whether that age group was bigger in later years compared to earlier years. So what we tried to do was look to this figure on the right and compare the densities of BMIs for the 55 to 64-year-old age category and see if there was a change from the 1980s to our most current time period, which was the 2010 and 2011 period. And this is why we had to add in the NHS1 data set, because NHS1 starts in the 80s. And so that allowed us to go a little further back in time and see if there was a change in BMI. If we had restricted our analysis to just NHS2, we could only start in the 1990s. And the problem with that is we weren't seeing a significant change in calorie intake by that time. So what we see is we have this one density, this pink one, and that was for respondents in the 1980s between the ages of 55 to 64. And what we see is when we move to the 2010 to 2011 period, we get this blue density, and we see a shifting to the right of the distribution of data, meaning that on average, people do seem to be bigger now than they were in the 80s. And this is controlling for age. So we don't think it's because of people aging in our population. So moving on to the next figure.
Natalie, can I just jump in with a couple of other observations? The first is that that distribution that you see on the right is actually very consistent with other data, including NHANES data that we published in 2015. So it is actually lining up with our expectations. And that is confirmed on the left, that those two slopes are the same. Even though there's a bit of a difference, we think is self-reported versus researcher collected, probably explains a good amount of that absolute difference. And the second thing, just for context on BMI, is that 18 to 25 is considered a healthy BMI by the medical community. 25 to 30 is considered overweight. 30 to 40 obese, and 40 plus is morbidly obese. Which has a clinical definition. And you'll see that in the 1980 data on the right, there were very few of the nurses had BMIs in that morbidly obese category. There's actually an 8-fold increase between 1980 and the 2010 data in terms of women in this data that have that kind of BMI, and a similar, not quite 8-fold, but increase in the nurses that are obese. So, what this data shows is that the distribution is flattened and moved to the right, and that is all very consistent with what other researchers have found with this and other data.
Right, exactly. So yeah, these results are robust to many data sets that we looked into. So if we move on to the next slide, the progress along our research was, we had two findings. BMIs seemed to be increasing over time. Caloric consumption did not. So we asked ourselves, what could be explaining this increase in BMI over time in our respondents? So we considered another pretty typical measure, and a reason many people believe you gain weight was maybe it's how much sugar someone consumes. The more sugar you eat, the bigger you are. So to try to evaluate that relationship, we looked at the proportion of fructose in someone's diet, and we tried, which is a type of sugar, and we compared that to their BMI. And that is seen in this figure on the right. And once again, we saw no discernible relationship between these variables. We spent a lot of time trying to understand the shape of the distribution of the data, and there just didn't seem to be a clear relationship between sugar consumption and BMI. What we noticed was this type of relationship persisted in a lot of different variables regressed against BMI. So there just didn't seem to be a clear explanation of why BMI was increasing over time. And that was very confusing to us because there seemed to be a lot of studies that have definitive conclusions as to why people are getting bigger over time. So we decided to take this analysis one step further and see what happens if we specified a model using the proportion of fructose, or how much sugar someone eats, against their BMI. Would we see a statistically significant relationship? And would this seem to confirm what we're seeing in the literature, which is that there are many statistically significant relationships that are associated with BMI? And if so, what does that mean for the rest of the literature out there? If we're finding statistically significant relationships with data sets that we find no clear actual discernible relationship when we plot it out, what does that mean for the field in general? So I guess the two takeaways from this are that we don't see a relationship between sugar consumption and BMI. And we didn't see a relationship between BMI and many other variables. So we think that the takeaways from our analysis that we'll discuss later on in this presentation can be attributed to many other relationships too, and that we really need to be careful when we're drawing inferences with these really large data sets. So I think, Anna.
Can I just point out one thing which is critical here, that because of the number of data points in that cloud plot on the right, you can find a statistically significant relationship between the proportion of fructose and BMI, and that's what we're going to discuss. Because even though, you know, by many measures, including just looking at that distribution, there is not a discernible relationship. What we're going to discuss is just how statistically you can create significant variables, and if you simplistically look at that, you may be led towards causative links that probably don't exist in reality.
Right, and that's a function of the fact that statistical measures of significance are normally assume normality in the distribution, and our formulas for trying to estimate p-values and t-statistics and other measures of significance are very dependent on the sample size. So the bigger it gets, the more likely your relationship is deemed to be statistically significant.
Yeah, and going off of that, so we did run a regression model with just fructose and BMI, and we did get significance, which in a lot of senses is what the standard for like publishing significant results, but we did want to look further. And so we specified 2 more linear models with a few more variables. And so you'll see in the first model that we tried, we chose some variables that were interesting to us, like age, cholesterol, number of children the respondents had, and how active they were, so how much exercise they get in a week. And then model 2 would be the same as model 1, but we did add vitamin C as an additional regressor. And we assumed that if the relationship between fructose and BMI holds, these models should be pretty conclusive in what they find. So we would have 2 significant results, hopefully, with the same coefficient sign, or that's what we would expect to see if there was an actual legitimate relationship between fructose and BMI. And something that we needed to be careful about is it's easy to not look at like the year of the survey and just run with all of the data. So you have 400 or 500,000 data points, which seems like really exciting because you have so much data. You think that your results will be more complete because you have more data, but you need to control for the fact that these are the same respondents, but also aging and in different years. And so what we did is we ran each regression in its respective year to see if these relationships held constant throughout all of the survey years. So if we go to the next slide and we look at the graph on the right, we'll see our results with model 1. And remember, model 1 has all of the same variables as model 2, and model 2 just adds vitamin C. And we've drawn lines here at 1.96 and negative 1.96. So anything that falls outside of these dashed lines would indicate a significant result. And we did plot what happens if you use all of the data at the very left of the x-axis. So you'll see we do get a negative relationship when we look at the coefficient of the t-statistic for fructose regressed against BMI. So if you looked at all of the data points, you would conclude that the relationship is significant and you're getting a negative coefficient, which would lead one to think that the more fructose they eat, the smaller their BMI, which is pretty counterintuitive, and we definitely wanted to investigate it further. So if we look through the data on the right, you'll see that not only is there some data that's not significant, so if we look at model 2 in 2003, that falls directly in between the red lines, so we wouldn't conclude a statistical relationship from the 2 here. There are some that switch signs, which would mean that your interpretation of fructose against BMI would change, which doesn't make a lot of sense. So if we look at from 1999 to 1995, basically, you'll see that model 2 is negative in 1995. for fructose, and it will go positive in 1999, which is indicative that this is not an actual genuine relationship between fructose and BMI. And there are not a lot of studies that will look at this kind of sensitivity, and we just wanted to point out that this is very demonstrative of our second pitfall, where it's very easy to conclude there's a statistical relationship when you have a lot of data points, and it may not actually be because there is a genuine relationship.
And so we just, we want to make sure we underscore the point that a researcher that would just look at model 1 would be very excited with those results. And, you know, the standard for journals, like those results can be replicated and, you know, they are showing a statistically significant relationship in every year. And so any researcher that's trying to find an association between fructose and BMI, or many researchers might publish that result. And what we want to point out is that with hundreds of thousands of data points, you really have to be careful. And when you find a result, whether it's intuitive or counterintuitive, you really have to test the model. Because, you know, we've looked at vitamin C and its relationship with fructose. You may think, well, there's a lot of vitamin C in an orange and there's, you know, a lot of fructose in an orange, but that correlation doesn't go high enough that we think there's a multicollinearity problem. And that just adding in vitamin C, there's no explanation why you get results that are so different from the model 1 results. So like Anna was saying, if a real relationship existed, it would be robust across model specifications and survey years. And the fact that many of the model 2 results are either insignificant or even negative is an indicator to us that a researcher publishing just model 1 would be.
Right. And building on that also, another thing we want to highlight is that oftentimes researchers will present different model specifications of the relationship to ensure robustness. So like what we're doing here, they may present different models, including slightly different variables to try to address bias issues. And if they find that in all of the different specifications, this statistical relationship persists, they'll draw the conclusion that yes, there is a genuine relationship between these 2 variables. And we are highlighting here that you can change the model specification, find statistical significance many times, and you could accidentally assume that, hey, a relationship exists when it may not. And we'll continue later on showing that this statistical significance, we lose it when we decrease the data size, which is evidence that the relationship could be drawn from just the sheer sample size, how much data there is. And so a typical robustness check that researchers use, which is to try different model specifications to ensure the robustness, is not actually that great of a robustness check when your data set is this large.
Thanks, Natalie. One quick question that showed up in chat is for Anna, who got all of our graphics together and has been working pretty high level with this data in R. The question was, you know, how did you create the graphics, or on what platform?
Yeah, that would be R, and ggplot is how all of these graphs were created, which is a great software, and it's pretty easy to use when you compare it to a lot of other coding languages when you need to plot a lot of data. And so I highly suggest looking into it. It's great.
All right, we're going to move on to the next slide. So the next slide introduces the second and last big data pitfall that we want to make sure researchers don't fall into. You know, as you know, the larger your sample size, the more likely you are to get statistically significant, or to find statistically significant relationships. So what we endeavored to do was to thin the data. So instead of, you know, hundreds of thousands of data points, we wanted to create data sets that were representative of the larger sample, but wouldn't have those same the same influences of a data set quite that large. And what we did was we used a bootstrapping method to select data randomly with replacement, meaning that the clouds ended up being more representative of the full set of data for n equals 10,000, 5,000, and 1,000. And what you see is the shape of the cloud of the fructose proportion relative to BMI for each of those sample sizes. And I think it may be worth just going back up 2 slides to slide 7. What you'll notice, I mean, you can do this visually, and if you could just go up 2 slides, is that if you take a look at the cloud for the full population, yeah, perfect. This is what all of the data looks like plotted, and you see it has that fan shape off the origin. And if you go down to back down to slide 10, you'll see that just visually the shape of these clouds should look fairly representative of the larger sample. And that's really what we were trying to do, is first bootstrap into decreased sample sizes that still would give you the same type of relationships and regression results as the larger sample, and then test whether the relationships you see, with the expectation that statistical significance would decrease, it shouldn't disappear if real genuine relationships exist. And so with that, I'll hand off to Natalie, who will show you what our results were there.
Perfect. Before we move on, we actually have 2 questions that I think we can address. The first is, how many times did you sample for your N? So for every thinning of the data, we did 1,000 replications. We actually calculated some statistics on each data set and found that there was very little variation between every replication. So the mean, the distribution, the standard deviation, et cetera, were all very similar for each bootstrap, each sample that we drew. And then these 3 figures you see on one of our slides is one realization of our sampling. So we had 1,000 of these for each sample size. And the second question was, were these sample sizes arbitrary? Yes, they were. We just chose random sample sizes to try to decrease the data to see what happened to our statistical inference when we had smaller sample sizes.
But it is worth pointing out that a data set of 10,000 can produce very significant results. These 10,000, 5,000, and 1,000 are not by industry standards considered small or non data sets that you wouldn't draw conclusions from. And so that's important, because we want to see what the significance of the relationships look like with the thinned samples that are still, generally considered to be valid data sets.
So once we thinned the sample, we tried to re-estimate our regressions. The idea was trying robustness checks by varying the model specifications didn't seem to affect our conclusions that there was a statistically significant relationship between fructose consumption and BMI. The next question was, would this relationship hold if we had less data? So what we did is we sampled from our data set different data sizes. So as Evan said, we had a sample size of 10,000, one of 5,000, and one of 1,000. And we re-estimated our models 1,000 times for each sample size we chose. This figure on the right plots the median T statistic for the relationship between fructose consumption and BMI. What we see is on the most left pane, that is our full sample. So that is the figure we presented a few slides earlier, which showed that there was statistical significance in many of the years for both models between fructose consumption and BMI. What's interesting though is as we progress towards the right, so as we re-estimate these models for smaller and smaller sample sizes, we were losing statistical significance. And you can see that by the little dots, which represent the t-stats for every different year, go closer and closer to this 0 line. Anything within these red bounded lines show that you lose statistical significance at the 95% confidence level. So what we see is when we reduce our sample size to n,000 data points, we lose a lot of statistical significance in model 2, and we start to approach the non-statistically significant area for model 1. When we reduce our sample size to 5,000, we've almost completely lost statistical significance for model 1, and we're starting to lose a lot of statistical significance for model 2 as well. And then, for model 1 as well. And then lastly, when we go to a sample size of 1,000, which as Evan pointed out, is a pretty large data set still, we completely lost statistical significance. And if there really was a true relationship between these two variables, we would expect the statistical significance to persist when we have reduced the sample size to 1,000. And this is really what we want to highlight and caution researchers against, is that you may think you have a statistical relationship because you might try various specifications of a different model and you might find persistent statistical significance between the relationships, but this could just be a function of the data size. And that's what we're seeing in our analysis, is that there wasn't a relationship, although it appeared to be. And that's because as we reduced the data size, we lost that statistical significance between the two variables. So our caution is that you can't, when your data size increases exponentially, you can no longer rely on typical and standard methods to determine whether valid inferences exist. You need to think beyond that, and you need to start doing more in different types of robustness checks. The first obvious one is to just plot the data, look at it. I can't tell you how many papers we've all read that don't actually show the data. So you have to trust the statistical inference that's presented in the final analysis tables. But the problem here is that it is so easy to manipulate these results. The next approach is one that we're trying to push forward, which is this idea of thinning the data, re-estimating the models with less data, and seeing if the relationship persists. We think this is a valid robustness check. It may not be a full robustness check, but it definitely can point you in the direction of whether you need to evaluate the relationship more. So if your data set decreases, you've resampled your data and re-estimated your model, and you're finding that the relationship doesn't persist as the data set size decreases, that is something of concern and something a researcher should consider before publishing results. And that's really what our presentation is focused on. This result isn't unique to the relationship between fructose and BMI. This is a problem that persists with big data sets in general that doesn't seem to be heavily acknowledged in many fields, and that we want to draw attention to.
Thanks, Natalie. I saw a question in the chat, just looking for a little more detail on what types of regressions were used here. If one of you wants to give that answer.
Sure. So I'm sure Anna can correct me, but we estimated log linear models, and we are not presenting results today that are robust to errors that would persist through the longitudinal nature of the data. The reason, and that would be in this all category. So basically, we're not controlling for a random or fixed effects type of regression, which a researcher should do if they're relying on longitudinal data. We're doing this because many fields outside of economics and statistics don't seem to take into account this persistent relationship in the data. So we're trying to highlight how easy it can be to manipulate data and rely on this data when you don't account for these things. But we've also presented our regressions on a year-by-year basis to try to eliminate that effect. We've done normal controls, we've tested for multicollinearity to try to make sure that we don't have much bias in our results. But the point here is not whether we are accurately capturing the relationship. The point was how easy it was to draw inference from probably a poorly specified model. And I don't know if you have anything to add to that.
No, that answered the question. It's a pretty simple log linear model with just multiple variables. There's nothing that fancy going on in here, and we did tests for multicollinearity, so we don't have any kind of interaction terms or anything at all in these models. They're pretty simple as far as linear models go.
The next question is kind of, I think, a general question of what is the threshold to consider a data set big data, and I would extend that question to then approach these pitfalls and test for them in your analysis. And again, you guys, Natalie and Anna, feel free to jump in, but I would say there's no bright line that says this is the relationship. There is, you know, clearly if you look at the full sample, there's, you know, a gigantic amount of data, and we can do a number of tests just to find how easily we can find any relationship you want with statistical significance. That's just the nature of this big data. But, you know, even at 10,000, if this were only a 10,000 data point data set, you're still finding a lot of Model 1 significance, and it's still quite publishable at those levels. And so it doesn't cost all that much for a researcher to bootstrap and do this type of analysis to check the robustness, to add model specifications and to thin the data just to test if what they're about to publish is actually what the data is saying. So rather than draw bright lines, I think, you know, when in doubt, these methods are certainly easy statistical checks to ensure that you're not publishing results that are largely driven by the data size. If there's nothing to add there, we have a couple more questions. The next one was, can bootstrapping methods be used to estimate the uncertainty and the significance of the trends? Natalie is our resident expert on bootstrapping, so that may be a good one for her to take.
So I don't know that we can answer that right now. We haven't tried to develop a method to estimate the degree of uncertainty. The first step in our research is just trying to address the fact that there is uncertainty, and the relationship isn't as clear as it used to be when researchers typically relied on smaller data sets. So what we're advancing here is a robustness check. We would probably have to do far more analysis to come up with some type of estimator of the degree of uncertainty. We're not purporting to that we've come up with that. All we're trying to say right now is that this is a problem. Here is a tentative way to deal with it. And we're encouraging researchers to try to think of ways to deal with this. And then we have another question. Did you consider some feature engineering, like calories relative to height or calories relative to mass? Perhaps those have more predictive power to BMI. Maybe I can ask for clarification. Oscar, did you mean as the dependent variable or as an independent variable, these other variables you're discussing?
And if he's going to type a response, I will generally say that we looked at tons of model specifications and looking at different variables and different relationships. And really what we found with this data is there are so many ways to find statistical significance in a very likely to be a publishable way. And so I don't know that we looked at those specifics, those specific variables, but I'm sure you're going to find a lot of the same relationships regardless of how you measure the different, you know, BMI or any kind of caloric density per height. Natalie, do you want to answer now that he's specified independent variable?
Yeah, sure. So yes, we did consider various measures trying to take a relative measure of caloric intake. So we also considered it with respect to total carb consumption, total protein consumption. We tried various transformations of the caloric intake variable to see if the relationship persisted. What we found was, yes, it did persist. We actually decided not to present these findings because caloric intake is very susceptible to the reporting measure, and we didn't want to be bogged down by this problem. So we tried to take a variable that was less likely to be susceptible to reporting measures than calories. So many researchers try to stay away from caloric intake in these types of analyses for that reason. And that's why we did, because that is not, the point of our research is not to explain per se why BMI is increasing over time. It is to try to show that it is very easy to find explanations for why BMIs are increasing over time when it doesn't actually appear that there is a relationship between the variables. Do we have?
So I saw there was one more question in the chat. I know we're running up against time here. Maybe we'll just address this question. And you know, Natalie, Anna, and I are all available on the Brattle website. So feel free to just shoot us an email, and we can to any one of us, and we can answer your questions. The last one was, do you believe it would be useful to blend or plot multiple n equals 1,000 bootstrap models? Natalie or Anna, what do you think?
I mean, that's a data visualization issue. So I guess we could have plotted the 1,000 t-stats because we didn't see much variation between them. You would basically have a lot of points all on top of each other. I'm not sure how useful that would be. So that's why we decided to plot the median of the t-stats to give an idea of where these variables were landing. I do agree that it might be helpful in future research that we plot also the boundaries of what these t-stats were to try to show the variation. But what I can tell you is that there wasn't much variation and the result was pretty consistent. As to plotting it, I don't know how helpful that would be. We can definitely consider it and go back, but because there was very little variation, I just don't know that it would show much more. It would give much more, it would be that much more informative.
All right, Kathy, we're going to turn it over to you if you have any follow-ups for us, or if we're ready to conclude.
Yeah, I think feel free to conclude. I had a summarizing question for you, which is, I think I have been sufficiently unsettled by these various findings, and that normally when you think about big data, I think, oh, more data will give you more insightful findings. And this has shown that that is not necessarily the case. So for our participants, what kind of advice would you give to when they're using data analysis to inform decision-making? How can they properly characterize their findings in data analysis such that the people who are making the decisions are properly taking those factors into account?
I guess I can start that, which, we have kind of a subtitle of this presentation of with great power comes great responsibility. 20 years ago, you couldn't dream of really effectively working with data sets of this size, but because of computer power, it's kind of secondary that anyone, with a little bit of knowledge can work with these types of large data sets. And what we really want to see is the literature evolve towards these methods that present not just statistical significance, but also robustness checks that say, I understand I'm working with a big and powerful data set, and my results are robust for this sample size. And I've tested it at least in these two ways, so that we can hand that off to the next level. Because the unfortunate part of this data set and nutritional research in general is that it's largely epidemiological data, where researchers can find relationships, they can find correlations, and unfortunately public policy has been reactionary towards that correlation. And a lot of policy recommendations are based on these epidemiological associations that are very small compared to, the epidemiological gold standard was smoking, where they found giant relationships between smoking and lung cancer that eventually turned the tide on that as a public health disaster. Here, the relationships are, 30% or 15%, and a lot of recommendations get based on those tiny relative risk factors. And that's what we find, say, with meat recommendations, that you have a 20% greater chance of getting cancer if you eat a certain amount of meat or processed meat or something. But the risks are so small, and that relative risk difference is, in my opinion, largely a function of the data and the data size. And what I would want to see before public policy recommendations are made or instituted is the epidemiological data passes on to researchers that can do randomized controlled trials and discover biochemical pathways that give causative explanations for statistical relationships that are found quite easily, as it turns out, in epidemiological data.
Right. To add to Evan's point, we find big data very exciting. We're data scientists. This is a great opportunity for researchers. What we're trying to caution against is to not be so reliant on typical measures of statistical inference. It could very well be that a relationship exists. All we're saying is that look at the data, think about the data, consider new robustness checks that didn't used to be an issue, maybe even 10 years ago. I don't know when. I shouldn't quantify that. But the point is most of us have been trained to accept that if a p-value is low enough, then the relationship exists. This is becoming increasingly a problem as p-values and t-statistics are very easy manipulatable when the data size increases. So the point is, big data is a wonderful tool. We just have to think more about how to process it and how to draw inference. We can't rely on old measures to draw inference because this is a new world. This is a new type of data. And we just have to be respectful of that and understanding of the limitations. And when we understand them, we can actually draw good and real inference.
Yeah, that's awesome. Thank you so much again for coming in and presenting. I think the title says it all. With great power comes great responsibility. And I hope that our participants can walk away with this message and really be conscious about the types of data analysis that they undertake and the implications that they may have. And thank you again for coming, and to our participants, happy hacking. Thank you.
Thanks so much.